Today we'll be talking about toy model superposition. Last week we talked about attention sinks. Um, this paper is probably a standalone paper, but it does provide good insight in terms of what's occurring within these models and tries to provide an explanation for an observed phenomena that we see with like language models, both language models and like just standard neural networks. Um, you don't really need a recap because this today, again, as I said, standalone. But we'll be talking about like things like features, um, what a privileged basis is, and then kind of their experiments that they run with sparsity and importance, and then try and see what like geometric structures emerge as a result of this superposition theory. Okay, so I guess first off is what is a feature? Um, features uh in this like zoom in paper, right? Um, and they provide like a variety of definitions, but there are some like standard properties that we want. One definition that some people might say is that like features are arbitrary functions, and I guess this kind of makes sense, right? Like these these neurons or these nodes are built by like an activation function surrounded by like a weighted sum. And it's just like this composition that occurs over and over again. But it's not really arbitrary because we do find that uh, um, like irregardless of model architecture or irregardless of the specific design choices, there are quote unquote features that um, are universal, right? And I guess another definition that one might have is that features is something that's just interpretable. And I think this definition captures something that we want with like mechanistic interpretability, right? I mean, interpretable is in the name, but it might be too broad. Like you have like these neurons and um, I think is it VGG? Yeah, VGG or yeah, VGG, which are like have been shown to be corresponding to like a dog's face, right? Um, so this arbitrariness is kind of out the picture already. Um, right. Another thing that people have seen is like neurons are specifically in control of curves, or like the outline of an image. Um, I guess other points or like for these specific plots, this would be like a neuron that maximally activates when you feed in an image. It'll maximally activate when there's like this curve that existing within the image, right? And again, we can see this throughout like different uh, image networks like ResNet or VG or VGG. I guess in terms of like language models, where like nodes are in control of a specific thing. A very famous example is like the Golden Gate Bridge, where um, you just have a specific neuron that fires when a Golden Gate Bridge is provided, or like if or a bridge is provided within the input.
Could you write something on the board?
What?
Are you gonna be using this room for the next gathering, whatever the hell?
Yeah.
Could you write something like Math 136 exam is this room? Because
Oh.
somebody changed the
Oh, sure.
room last minute.
Okay.
In case somebody's here.
It's in the other room. Okay, sure. All right. Uh, so then, with that in mind, like are features interpretable? Is this condition enough? You often find that there might be like features that you might see that isn't that like interpretable in the beginning, but after some more experimentation, that it becomes more interpretable, like a low frequency pass or filter or a high frequency filter. Um, so, this like interpretable definition, there's still some like issues with it. Being like what we might use. And so what the authors provide is like two kind of definitions. The first one is like features are neurons in a sufficiently large model. What does that mean? I guess that kind of like tries to answer what is the difference or functional difference between like a model with like, let's say, two hidden neurons versus a model with like four hidden neurons versus a model with like um, 200 neurons, right? Is there any difference? And in I guess like maybe in CST 311, people might say there's zero difference according to the authors. Um, these neurons do, um, and these different models, these neurons do possess like a difference, and it's that um, these features might not like perfectly align with each neuron, but they like as you compress it down, they become like a superposition, um, or the features become a superposition of previous features. So, like, what does that mean, and what does that look like? So, like in the case of um, I guess this like car example, you have like um, these neurons that are aligned or specific towards like identifying a window or identifying a car body. And what superposition is trying to say is that you just combine all these like feature aligned neurons to create a new neuron that's like in charge of a car, right? And this usually happens within like middle layers, since you want to create something or like you want to construct like this detector. Um, but you know, this like after you create this like detector, you still want to like propagate this information to the final layers, right? And in order for it to propagate to the final layers, this car detection feature gets spread across multiple neurons. Can you fix the resolution? Also record. Oh, I didn't record. Wait a second. Stop share. It should be recording. I'm not sure if feature resolution setting. Oh, how about the resolution? Is still, oh, sharing. Okay. How about now? Is this is it better? Jessica, can you see the full screen? Oh. Okay, settings. Share screen. I see. Let me see how I would Sure. How would I disable that? Okay. Um, right. Let me, uh, okay, there we go. All right, how's it now? Okay, cool. Where was I? Oh yeah. You might want to propagate this like car feature to the final layer so that like the model can predict um like if there's a car or not, right? And as a result, this like car detection feature gets spread across multiple layers, spread across multiple layers and spread across multiple neurons that might be polysemantic. And when we say polysemantic, this just means like a neuron isn't aligned to a specific feature, but like a mixture of multiple, maybe more basic features. So on the right, you can see uh like the second neuron here. The second neuron here is like a mash or a combination of more fundamental features um, like a dog's head here, or maybe like a car window here, right? Um, and when we say like maybe like a more fundamental quote unquote feature or like a feature that's aligned with a neuron, we call those like monosemantic neurons. Right. And so when the authors of this paper kind of say like, oh, it's features in a sufficiently large network. These like larger networks are basically representing neurons or have neurons that are representing the same thing as these smaller networks, but these neurons in these larger networks are just monosemantic. So if we go back, you know, if we go back to this like earlier picture, if this was larger, like if this layer here was larger, you can imagine that these like polysemantic neurons would be like the features in these polysemantic neurons are spread across um, the neurons of a larger model because they have more neurons to play with. And why do and this is like one evidence, right? This is the observed phenomena. Um, Polysemanticity is the observed phenomena. Another reason why people believe like a larger model um, might be, or like neurons of a large model might be sufficient as a definition for a features. This like paper called lottery ticket hypothesis, where like they have this like big dense network. As you can see on the left, it's like 100 million, and they get like an accuracy of 95%. And then they go through this like pruning process of yeah, they go through this like pruning process in which they like set the weights of the model or specific neurons of the model and set it to zero. And then after setting it to zero, they can construct a sparser network that achieves the same accuracy, right? And I guess another perspective is that all we're doing is condensing this like very dense large model with all their like mono quote unquote somewhat monosemantic neurons, condensing that into like a sparser network where each neuron is in control of a bunch more features. Okay, so that's one definition that they kind of use. The other definition is that features are some vector or some direction in activation or hidden space. Um, and this is just so that we can like analyze uh, what features might be. And the motivation for this kind of definition or this property, at a high level, is this like very famous example of uh, latent embeddings. So, you know, the most famous one is just like you have like this word embedding matrix that embeds a direction for king and queen, and the king and queen direction might uh, be like, or I guess like the difference between these two directions would control like a gender direction or gender vector, right? And then the difference between like the king direction and the man direction, this might be like a royalty vector. And these vectors are orthogonal to each other because these features are, they're different features, right? They're different like um, concepts. So yeah. That's like the high level. The other like high level motivation is just that there's a lot of literature on this like linear directions being like um, causally encoding certain behaviors. So in our case, like this linear direction uh, like encodes refusal, right? In which like this writing propaganda and how do you make a bomb possess the same like subspace, and like writing a harmless prompt possess the same subspace. Okay. So with these two features in mind, or with these two like definitions or properties in mind, we can like continue further um, and talk about like some of the findings of this paper. All right. I guess, yeah. Uh, you know, the authors are then interested with these two definitions to see whether or not there's some linear transformation between like a very large model that has like monosemantic neurons versus like a very small model with um, like polysemantic neurons, and see like what the weight matrix like properties of that weight matrix might possess. Okay, so definitionally, we'll just define like uh, I guess this X to be in R of n space. Since we're taking this X to be of R of n, and this X will be like a feature in some like high or very large network, and each element in this vector represents like a feature, right? Um, and then when we like try to do or project this like high dimensional feature vector to a low dimensional space, um, we'll try and see like what the weight matrix might look like. And specifically, we'll look at the columns of the weight matrix. Since the weight matrix is m by n, um, we can kind of like view this as like, for those who know, it's like a encoder um, type model, where you have like a bottleneck um, as a result of inputting this high dimensional feature vector X. Um, and the reason why I say like the columns of the weight matrix are your feature vectors in this low dimensional space is because um, there are n uh, columns, right? And each of these columns live in m-dimensional space or low dimensional space. Um, Versus if you look at the rows live in n-dimensional space or high dimensional space, and there are m of these vectors, right? And so what we're interested in is specifically what happens with these columns. Okay. So like a natural question that arises from the perspective of a vector, or like viewing features as a vector, is that what is like, are there special vectors? Or like, when you first learn linear algebra, you might learn things like a basis, right? And the authors try to provide like, an explanation of when there might be a basis that's like quote unquote interpretable or quote unquote privileged, versus when it might not occur, right? And this is as a result of like model architecture. So when superposition occurs, I guess first, um, the superposition occurs in low dimensional space when there's like a dot product between feature vectors, and these feature vectors are non-zero. And uh, the only reason why we can like interpret or understand these features for like a transformer or language model or like a very simple neural network is because there's this privilege basis, right? There's this set of vectors that are very special. And these like special vectors emerge as a result of um, our activation function. So that's why I can like understand the hidden space. Otherwise, like um, you know, any two vector, uh, like otherwise, like trying to understand the neuron um, is impossible because uh, like your feature vectors won't align with the specific neuron. Um, and so in the case of like a non-privileged basis, um, these are just like uh, 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 scenarios or models where you can't uh, interpret um, or there are no like special vectors within the space, and that usually is as a result of um, like the fact that like the space that you are working with is rotationally symmetric. So if you apply like a rotation matrix to a linear model and then try like understand it, uh, you can like apply the same rotation matrix, just the inverse of it, and you'll just get back to your original space. But you can't do this with a privilege basis, right? But yeah, so yeah, as I said, the privilege basis or your activation functions make it such that you can understand what the vectors are. Um, Otherwise, you can just apply a rotation matrix. So why does a superposition occur, right? This like combination of features, why does this occur? It occurs because at a high level, there are just a lot more features you want the model to learn or express um, than like the dimension of your activation space. Um, you can imagine like training like a very simple neural network on like ImageNet, for example. And there's like thousands and thousands of classes. But each of these classes might have like a feature that's shared among other classes. For example, you might have like a dog's ear that's, this ear thing is common between like other animals. And then you can like continuously like dissect each of these images and kind of like construct your own feature. Um, and so, if some people might be like, oh, all you have to do is construct a really, really large network. But there's just seems to be like you can always construct a new feature later on. And in terms of like polysemanticity, with regard to this privilege basis, polysemanticity is when the dot product of like your feature vectors are non-zero with these special basis vectors. Um, and as I said before, superposition occurs because these like special basis vectors, you can only have like n orthogonal vectors, but you want to express like m or you have m orthogonal vectors or low dimensional vectors, and you want to express like n features. And so, um, the model has to figure out like how do you go about embedding these features within this low dimensional space. Um, so again, like I said, you have this language model. Um, it has like this embedding matrix with like a dimension of however much you want. And then the vocabulary size, which is the like around 50,000 or 50,000 plus, right? And typically this embedding dimension is much smaller than the vocabulary size. And so, my original thought of like solving mechanistic interpretability um, was just to create a much larger network because in that case, you just have monosemantic neurons. But as I said before, you can always construct new features. So one thing might be like the concept of a person, right? This concept of a person, um, there might be one vector for this, but people have like different attributes, right? Like prominent figures like Jim Carrey, right? That might be a feature, and they're like correlated or features that are connected with that like person's name. Like Jim Carrey's funny, Jim Carrey's white, he's a comedian, right? So even if you create like a language model with 50,000 words, there definitely going to be like an exponential like magnitudes more amount of features that um than just like your vocabulary size. Oh, and the other thing, like the property that causes superposition to occur is this idea of sparsity, right? You can imagine like where like not all features are present at like in any like one forward pass, and in fact, like typically there's only like maybe a few features that are present. Um, and because of this, the model can make use of this fact that these like input vectors or like your image might not possess both like a shark um, and a building at once, right? So like let's say you have like ImageNet data set, right? Or yeah, like the data set corresponding to it. You have like a bunch of classes. Again, you have a mammal, placenta, carnivore, yada yada yada. The feature of like a dog's ear will not or probably not occur with like the mast or the sail of a sailboat, right? And like in terms of training, you're probably not going to see uh these two concepts or features occur at the same time. And that's what we mean by sparsity. So again, A, the features are sparse, and then B, each of these features, there's just like a lot more features that you want to express um, in your hidden space, activation space, low dimensional space. And as a result of these two facts, superposition occurs, right? So with this in mind, how do you construct a toy model? These authors are then just like um, construct like an autoencoder. So again, like let's imagine we have like this larger network with an n-dimensional vector where each element x of I is a feature. This x vector is going to be sparse, and we're going to have this autoencoder setup. Okay. So, what does sparsity mean in terms of math? The authors define sparsity to be like, uh, again, like this high dimensional vector to be zero with some probability S of I, and then otherwise, this vector will be sampled from the uniform, or the elements of this vector will be sampled from the uniform. And when we talk about sparsity, a one hot encoder or one hot encoded vector, so just like a one with all zeros, will have a sparsity of 100%. And like a vector with like all numbers, also called a dense vector, will have a sparsity of 0. Okay. This is just like a geometric picture that kind of like in case this is like a perspective that you might appreciate. This is a geometric picture of how do you kind of like visualize the probability um, of these vectors. So if the vector of x in R of 3 um, has all zeros, that would be a probability of s cubed. If a vector is aligned with one single uh, axis, it'd be 1 minus s times s squared, because only one element is non-zero. And then they can continue this forward. So if the vector is on some edge with like one element equals 0, then it's like 1 minus s squared times s. and then any vector within this box that's not aligned with any of these coordinate vectors, or will be considered as 1 minus s cubed moving forward. The other thing that they define is this like concept of importance, right? You can imagine like, why do you have this concept? You can imagine like a neural network being trained on like let's say ImageNet again, right? ImageNet has like thousands, like a lot of images of dogs, right? Like so much more dog images than like a sailboat image. And so if you have like training data that's like disproportionate, then obviously your features that the model learns is going to be disproportionate. And so like there's like features that become more important as a result. And at least for this paper, they define like importance uh, as a product of a matrix I of I and multiplied by their feature x of I. And I of I, you can be viewed as a matrix, can be viewed as a function that takes in x of I, and I is just defined as some number, usually a fractional number to the power of I, where this fractional number um, to the power of the index I. Okay, so the model that they want to look at is a very simple model, right? It's just like first they have like this bottleneck, h equals to some weight matrix times x, and then they multiply this bottleneck by the weight transpose, so that you can reconstruct the original x. And they kind of analyze this weight matrix in two cases. The first case where you have just a linear model with no activation function, and then you have a ReLU with activation functions. This doesn't mean that the analysis, like their analysis of the weights are going to be privileged. This just means when you like update the loss, like when you train this model, you have to take into consideration ReLU. And then the loss here is just the mean squared error loss multiplied by some importance value. We can kind of see it better with like a diagram. So in this perspective, right, we have like an autoencoder that constructs, projects this high dimensional X, brings it back down to this low dimensional bottleneck, and then brings it back up to this high dimensional space. And we're trying to reconstruct this feature vector, this high dimensional feature vector. Okay. And in terms of importance, you can see that like this concept come into play with this loss function. So like if we have like this importance of 1, 0.5, and all zeros at the end, the only thing that contributes to the loss function will be the first index and the second index. And obviously we want to minimize like greatly minimize the first like difference, because it has a higher importance value, and also it's just a larger number because you don't multiply by a fraction, right? So you can kind of see how like this importance value comes into play. And with this in mind, this loss functions get summed up over the entire index of the vector or the feature vector, and then you also sum up over every single training example X. So here, you have a different importance function here. It's like 0.7 to the n here, or I, right? And if you like graph it out, there's going to be basically like a geometric sequence where, if you're in the first index, you'll have the highest importance, and then it like exponentially decreases, or power law decreases to 0, right? So your last feature might have like is not important at all, but like the first 5 features will be very important. Okay, the fun part kind of starts now. And the first experiment that kind of runs is this like idea, like example is that they have like this like 5-dimensional input vector X, right, with like 5 features, and they want to embed it within a smaller, lower dimensional, two-dimensional space, right? And they kind of vary the sparsity. So when it's 0% sparse, this like input vector is completely dense. All 5 of its elements has a number, right? How do you represent all 5 of these elements, right? And you can see that it doesn't, right? It just prioritizes the first 2 important feature vectors. Because you can only you know because all 5 features occur at once. You can't express all 5 features that at once. So again, to minimize the loss, the model opts to express the first 2 important vectors. But then like the authors start to like increase sparsity. So when you train this like ReLU autoencoder, they like in the training data, like 80% of the feature vector is sparse. So that means that like uh maybe like 1 in 5 vectors will have, or 1 in 5 elements will have like an actual number, and all other elements will be 0. And you can start seeing that there's like the model is more willing to make a risk with expressing the lesser important uh, uh, vectors or feature vector, right? um, and this is because these feature vectors and high dimensional space, they don't co-occur as often. And because they don't co-occur as often, the model's like, hey, let's just like take a chance and express them, because it minimizes our loss further than just like expressing the 2 orthogonal vectors. But you might still see this like the fact that like these what? Oh yeah, you might still see that like I think one important thing with this like middle graph is that the vector, I guess like the most important vector, is going to be orthogonal to the least important vector. And this is because your most important vector is going to be, your most important vector, if in terms of like occurrence, right? In terms of like this low dimensional space trying to express this uh, um, feature, you don't want this both like the most important vector being expressed and the second most important vector being expressed, right? Because then if those 2 vectors occur at the same time, right, then you would just like get a vector of 0, right, since they're in the same subspace, right, or on the same line, and that would just cause it to have, or I guess these 2 vectors. This will just cause the model to, I guess, maximize the loss in that case. And then in terms of like, if you continue to increase sparsity, you just have like a greater amount of interference. And this interference is just defined as a dot product, where you can no longer express these high dimensional feature or elements as orthogonal vectors in low dimensional space. And then in this instance, right, they continue to like look at a further example. Obviously, you can't plot vectors in 5 dimensionals in 5D, right? But you can like analyze and look at the columns of the weight matrix. So this is where that comes into play. They specifically look at weight transpose times weight, and then try and see like how that, how this like the columns magnitude change as you change the sparsity. And generally speaking, you can see that, if your feature vectors are very dense, then you'll see that only the top five uh, most important vectors in high dimensional space gets expressed. But as you increase sparsity, um, the model is more willing to take that risk of allowing superposition and allowing this like expression of the other 15 not as important feature vectors. Um, and in terms of like the I guess weight transpose weight, or like the dot product, or gram matrix, uh, you can see that obviously you're going to have the highest dot product between on this diagonal because your dot product yourself. But then off diagonal, there's going to be a lot more interference as you increase sparsity. Okay. And then after some math, you can kind of understand, like, you can separate this loss function into two components. The first component is like the benefit of representing a feature. And the second component is um, what we call interference, or like the dot product between one feature, or one, let's say, row of that input vector and a different row of that input vector, right? And we obviously want to minimize this loss um, so that the model like attains a better representation. And after some math, or I guess under certain conditions, you can like view this as a generalization of the Thompson problem. So if you imagine that like all these features are equally important, equally sparse, and are independent, and then assume that the column vectors uh, all equal to 1 with the bias equal to 0, you can do some calculations so that the first term is equal to 0 always. And so the loss is just reliant on this interference. And if you want to minimize this interference, this is similar to minimizing 1 over the difference, or 1 over the root of 1 minus the dot product. So this like dot product between the features is similar to this, which is similar to this, which is similar to the potential of like electrons on a unit sphere. And the whole problem with the Thomson problem, or the whole like thing about the Thomson problem, is that you're asking how do you pack the most amount of electrons on a unit sphere such that this loss is minimized, or this potential is minimized. This is well understood, and you can kind of see like certain geometries emerge as a result of this Thomson problem. And so under this lens, do we kind of see something similar occurring with the uniform sparsity case of our network? And this is what we look into, like the geometry of superposition. So they first define this like dimension of like of expressing a high dimensional feature, right? Where the numerator is how much this features is represented in your low dimensional space, and then the denominator is that defines like for this like feature, how many other features is being shared, right? So d of I, this I index, is going to be the ith index of your input vector, or the ith column vector of the weight matrix, and so it's like the ith feature. and is asking, what the dimension of the, ith feature lives in. Um, uh, Benjamin Garrotti provides like a good example of like trying to understand this dimensionality, um, their definition of dimensionality. So like if you have like you're trying to express two features in a single dimension, you have like this diagon shape, um, where these two vectors are opposing one another, um, and like the dimension in this instance will be 1/2. So some other examples is like this triangular example where you might want to express three features in two-dimensional space. So you're projecting a vector from R of 3 to R of 2, and the dimension of the first feature in high dimensional space um, is going to be uh, embedded within a 2/3 dimension, because it shares this space with two other vectors. And as a result, it forms this like triangular shape. Okay. Wow, this is okay. So let me just go step by step. Um, Basically, the authors then show this like geometry, um, or like this y-axis is like your dimension, and then the x-axis is a sparsity of your input vector. Um, and what you can generally see is that when the model is not sparse at all, as we've seen previously, when it's dense, um, the uh, dimension, or like if you're going to express uh, like vectors, uh, you can only select like the first few vectors to be expressed. And you can kind of see this with like uh, here, right? So let's say like your sparsity is equal to 0, for example, right? Um, and then like, or in this case, they embed 400 features into, I think, a 30. Uh, so they go from R of 400 to R of 30. And they want to see like what the dimension is of each of the like first, I guess, 30, or each of the uh 400 vectors, right? And you can generally see that because it's dense, because the input vector, the elements of the input vector, they occur typically at the same time, right? All like the, I guess, lesser important features. So in this case, might be like 30, or like after 30. So like, um, 370, all the other 370 vectors won't be embedded at all, right? And so they won't be aligned with any basis. Um, and this is where you have like this dedicated dimension, um, as we've seen earlier with like on the left where you had like that dense weight transpose weight matrix or gram matrix, and you just see like the diagonals being the only um, uh, elements that have a dot product that's not zero. But as you like increase sparsity, right, you can kind of see like different geometries emerge. So I guess the perspective with this like 3/4 or this like tetrahedron is that each of these tetrahedrons live in some like its own subspace. So like its own like three-dimensional subspace, and each of these are orthogonal, and then you just project these down into 2D to create this like feature geometry. I remember trying to reconstruct this similar to Benjamin Garrotti, where he was talking about like creating these like very beautiful geometry images. And I can definitely say that uh, uh, it's not a PCA basis. They use some other method or low dimensional projection method to construct these feature geometry. Oh, one thing to note as well is that you might see like these line segments. These line segments are going to be the magnitude of an interference between uh, any two features. So as you increase sparsity, different geometries emerge, different optimal geometries emerge. Um, One thing that the authors say is that you have like this co-occurrence between um, like a triangle uh, geometry and a diagon um, around here. And as you transition between like different sparsity levels, there's going to be a lot of co-occurrences. So like with this uh, image here, you can obviously see like this like square antiprism geometric structure emerge in tandem with like this pentagon, in tandem with uh like this soup of uh I guess like this weird you know uh circle or a bunch of nodes that are in place. And then the general structure will be a pentagon or a pentagonal structure. All right. And again, like they don't live on the same like circle. I think that's a wrong perspective here. They just live in some high dimensional subspace. Here would be like a uh uh one dimensional space in high dimension and like the 400 dimension, and each of these are orthogonal to one another. Um uh and and yeah. And then they just like project it down to two dimensions to like visualize this. Same with here, where you have like these triangles. Each of these triangles live in some high dimensional or two-dimensional subspace in high dimension that are orthogonal to all these other triangles and all these other like digons. But like during to like actually visualize it, you would project it down to two-dimensional space. And then as you get like features that are much, much, much more sparse, we have this weird like bagel-esque shape that emerges. And yeah, that's about it. Um, Thank you for coming.